Excellent. So let's continue. You know, well, to start with, I'm going to just complete the discussion we had almost completed at the end of the last lecture on describing how you get geometries dual to fluid dynamic flows. I've written down the answer to first order here. So maybe I should just start with a brief reminder. We were trying to find a gravity solution dual to arbitrary fluid flows. The idea we started with was to make a gravity version, an ADS-CFT dual version of the notion that fluid dynamics is locally thermally equilibrated, but with varying parameters. So we started with a geometry that we wrote down a geometry that was foliated into tubes. Along each tube, the geometry was more or less identical to the tube of a geometry of a black brane at a given temperature and a given velocity. But we allowed the values of these temperatures and velocities to change as we moved along the boundary. So tubes were labeled by where they hit the boundary, and we wrote down a spacetime foliated by such tubes. And then we used that as the starting point for a perturbative expansion for generating a solution to Einstein's equations. It turned out that Einstein's equations can be decomposed into dynamical equations and constraint equations. The role of the constraint equations in our procedure was logically distinct from the role of the dynamical equations in the same procedure. The constraint equations weren't equations that allowed us to determine the corrections to our starting ansatz in terms of the starting ansatz. Instead, they were equations that constrained the allowed starting point for perturbation theory. The nature of the constraint equations was simply the statement of the conservation of the boundary stress tensor written in terms of the fluid variables. Okay? So the constraint equations gave us the equations of hydrodynamics. The dynamical equations, on the other hand, had the following role. We took the metric of the solution that we were really trying to find, and we have this counting parameter epsilon there. We started with G0, the ansatz metric, that was this foliation in the tubes, and then corrected it order by order in epsilon. So this guy was written entirely in terms of u mu of x and t of x, and the constraint equations constrained this and therefore constrained these functions. Okay, and the nature of the constraint was simply del mu t mu nu equals 0, where t mu nu was at leading order the expression for the stress tensor in perfect hydrodynamics with the equation of state of n equals 4 Yang-Mills. Okay, on the other hand, the dynamical equations were used to determine G1. Okay, so they didn't impose any constraints on the starting point. They just allowed you to continue your perturbative expansion given the correct starting point. Okay, and we talked about how we could uniquely determine G1. There was a unique solution to what G1 was in terms of the temperature field and the velocity field appropriately defined. Okay, we discussed how we could determine the tensor sector of that solution, and it's a similar procedure to determine the solution in the 3 and the 2 1s that we wrote down last time. All differential equations turn out to be easily solvable, and the net result at first order is the metric that I've written down on the board here. This metric here has all the terms above the dotted line are just the ansatz metric G0 that we started out with. Okay, but then this metric is corrected with G1. Everything below the dotted line is G1. This was the solution in the 5, where this big F function was, I can't even remember now, but obtained by the integration of the differential equation we had last time, r to the 5 r squared from RH to R. Okay, I could find a more serious expression for this by, it's the function that we had last. Let me write it down. It's some function obtained by that integration, but we've, okay, so f of r is equal to r to infinity dx x squared plus x plus 1 over x and x plus 1 x squared plus 1. Okay, some known function. This is the solution in the tensor sector, the solution in the 5. This was the solution in the 1, and this was the solution in the vector sector. Okay, so we've got the full solution to first order, and it's uniquely determined in terms of our starting velocities and temperatures. Okay, so this is how we implemented this perturbative procedure to first order in the derivative expansion. Any questions or comments before I proceed? Okay, now once you've done this to first order, it's a simple matter to move on to the next order. Okay, so what we've done is to find G, we know what G0 is, and we've determined G1. So we take G0 plus epsilon times G1, plug this configuration into Einstein's equations. You do this in Mathematica, and you say, you expand the answer plus order epsilon cube. So don't keep terms of order epsilon cube higher. Okay, terms of order 0, epsilon to the 0 and epsilon to the 1 don't appear, because you've solved the equation at order 0 and you've solved the equation at order epsilon to the 1. But terms at order epsilon squared do appear. Okay, those give you new equations. Once again, these new equations can be divided up into the constraint equations and the dynamical equations. Once again, the constraint equations are simply the statement of conservation of the boundary stress tensor. Once again, the constraint equations have an explicit factor of a boundary spacetime derivative. This derivative pulls out an explicit epsilon. So the constraint equations only depend on T mu nu evaluated up to first order in epsilon, because we keep only terms up to second order in epsilon, but there's an explicit epsilon from this derivative. Therefore, this constraint equation is an equation that you already know if you know G0 and G1. But we do know G0 and G1. Okay? So all we have to do is to take this metric that we've already determined, compute its dual stress tensor. So now what does this dual stress tensor evaluate? So from the first order metric, you just use the usual rules of ADS-CFT to evaluate the first order boundary stress tensor. And what do you get? Well, of course you get the 0th order part as before, n squared times number times t to the 4 times 4 u mu u nu plus eta mu nu. Okay, but you get a correction. This correction came from G1, this new stuff that we had here. Okay, what does that correction evaluate? Well, it evaluates to, it's got to be a first derivative order. In order to make up dimensions, there has to be a t cube. There's an overall n square outside. That's just the reflection of the fact that there's an overall 1 over Newton's constant outside everything we're doing. Okay, then it's got to be a tensor expression. It's got to be an expression for the stress tensor in Landau gauge, and it has to be traceless. Has to be built out of velocities and temperature fields. Basically, there's a unique possibility for this answer. It's sigma mu nu. Okay, and this comes with a certain number. So the only thing that this computation was the details of the computation were needed for was to evaluate this number. Okay, you can evaluate the number. It turns out to be something. The value of that number is such that okay. So now this whole thing here, as we discussed in previous lectures, has a name. It's called the shear viscosity. Minus of this is called the shear viscosity. You evaluate the shear viscosity, divide by the entropy density, and you find the famous value of 1 over 4 pi, in agreement with the by now classic predictions of Starinet, Sohn, Koftun, and all the Seattle and related group who worked on this 10 years ago. Okay, so the first order corrected stress tensor is simply that of a perfect fluid corrected by a viscous term, with a predicted value of the viscosity. This prediction comes out of Einstein's theory of general relativity. Okay? So in order to carry on our second order calculation, we take this first order stress tensor, we evaluate the constraint equations. The constraint equations have to be, when you put them on Mathematica, they have to be, but you can check also that they are, simply the statement of conservation of this stress tensor. Okay? So now you adjust your fluid data locally to satisfy this modified fluid dynamical equation, and then solve for the dynamical equations. Just use the same procedure that determines G2. Okay? It's a bit tedious, but not terribly difficult to do this, and you find an expression for G2. I'm not going to write it down, it's because it involves many functions, all of which are elementary in the sense of the integrals over elementary functions, but a bit tedious to write down. Once you have G2, you can then compute the stress tensor dual to the metric G0 plus G1 plus G2. Okay? What can you get? You get plus T square times other terms. These other terms are terms with two derivatives that are built out of temperatures and velocities that are transformed in the 5 of the preserved SO3. It turns out that just on general grounds, by demanding conformal invariance, and this was shown in a paper by Bayer, Sohn, Starinets, and Romashke, I believe, Stefanov, that just the constraint of conformal invariance restricts possible corrections to the second order constitutive relation down to 5 terms. This 5 is to be contrasted with the 10 that we found, if you remember, from our general analysis of the first lectures, for the most general possible allowed constitutive relation for a non-conformal fluid. Okay? So it has to be some combination of these 5, but gravity gives us the particular combination of these 5 that comes out of Einstein's equations. Okay? Now if you wanted to, you could carry this on to third order. You would use the constraint equations would be conservation of this second order corrected stress tensor. You'd solve the dynamical equations, you'd get the third order corrected metric, then you'd find the third order corrected stress tensor, and as you can see, you could go on forever. Okay? So this ends my description of the process you can use to generate the space-time solutions dual to fluid flows. Okay?
What happens when you run out of T's to soak up the...
You get 1 over T's.
Then it's, but it's only valid at high temperature.
Yes, this is an expansion in 1 over T. You should think of this with an overall T to the 4 outside. And this is 1 over T squared. Okay. Any other questions, comments? Okay, excellent. Okay. Now, we have about an hour and a little bit more left for these lectures. So I'm going to switch modes of lecturing a little bit. Yes, please.
Do you get logs of T with some other scale? Or not in this kind of system?
It's a good question. Do you get logs of T? Well, certainly we didn't to second order where the calculations have been systematically done. I suppose there's a possibility that at fourth order, where you hit the Weil anomaly, you'll get a log of T. In fact, that may be the role in life of the Weil anomaly for this, for this expansion. I don't know.
But your boundary metric is flat.
No, okay, yes. So far what I did is to describe the answer for a flat boundary metric, but it's a simple matter to generalize this to describing fluid flows and an arbitrary boundary metric. Okay, and anyway, the anomaly can have consequences even for flat space.
No.
The log of the Graham-Pfefferman expansion probably implies a log of the temperature, would be my guess. It's a good question, I'm not sure. Yes?
You say it appears at fourth order, but the first term of the Weil anomaly would be some Ricci scalars, would be 2 derivatives, no?
No, that's in 2 dimensions. In 4 dimensions, the Weil anomaly is R way down. It's 2 powers of R, just from dimensional analysis. Weil anomaly is a statement of what the trace of the stress tensor can be. 4 dimensions, the stress tensor is dimension 4. Okay, other questions, comments?
So for log, you need another scale, right?
What?
For log, you need another scale.
Yeah, what's going to happen here is that, what could happen here? It's going to be the fact that this thing right, is not exactly conformally invariant because it's violating conformal invariance. So somehow this will depend not just on the conformal structure of the metric, but actually the scale of the metric somehow in that log, I guess. But it's a good question. I don't know the answer. I suspect the answer is something interesting, but I don't know the answer. Yes?
Is this expansion like a 1 over R expansion and near the boundary, or?
No, this expansion is not the same as the Graham-Pfefferman expansion, if that's what the question is. Because, you see, if you just look at this, the 0th order term here, it has all powers in an expansion in 1 over R. This function f of b of r is a complicated function. Okay, and these functions are even more complicated functions. This integral is not difficult to do. You can evaluate it. It's 1 by 4 log of 1 plus r squared into 1 plus r squared by r to the 4 minus 2 arctan something. You see, if you took it and expanded in a power series in 1 over r, you get all powers. So what we're doing is not the same as a Graham-Pfefferman expansion. But it's a very good question, and let me pause to reflect on that. You see, these mathematicians, Graham and Pfefferman, proved this very interesting theorem about solutions to Einstein's equations in ADI space. The theorem they proved, which is sort of obvious from a physicist's point of view, is that if you take if you know the boundary value of the metric and its first radial derivative, which is roughly the boundary stress tensor. Okay, the extrinsic curvature of your slice, which is roughly the boundary stress tensor. Then this data is sufficient to integrate in radially to completely determine any solution to Einstein's equations. Okay, and the power series expansion that does this is called the Graham-Pfefferman expansion. Okay, now why is this obvious from a physicist's point of view? From a physicist's point of view, it's saying something pretty obvious. It's saying that we've got a second order differential equation. So 2 pieces of data on a slice are sufficient to determine the solution. But these guys did it carefully, so we know that it's not just intuition, it's true. Okay? Now, so from this point of view, if you know the boundary metric and you know the boundary stress tensor, you get a solution. Graham and Pfefferman even showed that you could find the solution up to a finite point in R. Okay, so a solution exists up to a finite point in R. Okay? So if you were thinking in Graham-Pfeffermanian language, you might think, well, there are solutions of Einstein's equations or solutions of the dual field theory for every functional value of the stress tensor. That sounds really odd, because a functional value of a stress tensor is a function of x and t. So if there was a legal solution of gravity for every stress tensor as an arbitrary function of x and t, that would mean that this field theory we're dealing with has no equations of motion. You can put arbitrary time arbitrary time dependencies at will. That's not how field theories behave. In field theories, you're supposed to specify an initial condition, and dynamics tells you what happens in the future. Okay, 1 second, please. Okay, so now, how does our procedure get around this? There's something really important that we did here that I want to emphasize again. The really important thing is that we demanded regularity of the future horizon. What happens is that the Graham-Pfefferman procedure can always be carried through, but generically it gives you a bad singularity. And then you stop and you treat that as not, you don't know what to do. Our philosophy is those singularities are not allowed. They're reflecting the fact that you're dealing with an illegal solution. Okay? The demand that there was no singularity was this demand in the integration of the sigma mu nu. There were 5 functions worth of such demands, because sigma mu nu has 5 components. Okay? So of the 9 components of the traceless stress tensor, we put 5 additional constraints. So that's 9 minus 5 is 4. So we get a 4 parameter set of solutions labeled by a velocity and a temperature rather than the full stress tensor. So you see, from the Graham-Pfeffermanian point of view, the key point is that the principle that determines boundary dynamics is the absence of singularity somewhere in the bulk. Okay? And it's clear you wouldn't see that since these singularities happen at finite distance from the boundary, you would never see this in a power series expansion. Okay, yes please.
From the
Just from the view of gravity, you have constraints, no?
Yes, you have constraints, but the constraints are 4 in number. If you have 4 constraints on 9 functions, that still leaves you freedom to specify 5 functions of time arbitrarily. That's still not good enough, still not like a field theory. Okay? Because we eliminated 5 degrees of freedom by the constraint of regularity, now we have 4 functions which are arbitrary functions of space and time, but 4 constraints. So we've got dynamics like a field theory should. Okay? So it's working very beautifully. Dynamics is being generated by from this admittedly odd Graham-Pfeffermanian point of view. Dynamics is being generated by the principle of regularity in the center. Yes.
Is there a way to count this? How many constraints you get from non-singularity?
Yes, it's 5.
But in this case, or you
what?
Could you argue from general principles that non-singular solutions should be?
Well, in this, I can argue that in every order you will get 5 constraints. You see, because just at the technical level, of the differential equations that we solve, only one of them, namely that in the tensor sector, has a constraint from imposing regularity. That's why I showed that one in the example that we evaluated. And so that's the 5. But actually this counting now works in every dimension. Let me show you that. Suppose we were in d space-time dimensions. Okay, so what is the number of components in the stress tensor? So that's d in a d plus 1 divided by 2 minus 1 because it's traceless. Okay, what are the number of constraints that we get? Well, we get the number of constraints is d minus 1 in a d by 2 minus 1. Let's check in 4. That's 3 in a 4 by 2, so 6 minus 1, 5. This traceless symmetric in one lower dimension. Now, I hope I can do this in real time. Okay, let's subtract this from this. So the 1's cancel. We take d common, so we get d in a 2 by 2, which is equal to d. That's the number of variables of fluid dynamics, the number of constraints. So the regularity condition always cuts down the free data to that number that constraints give you evolution equations for. Okay, other questions, comments? Excellent. So, now we're going to have to switch these lectures to seminar mode, okay? We're not going to look at every detail of everything we're saying, just so that I can tell you many different things. I'm sorry, I don't like it when people do this to me, but that's life. Okay. Fine. So, there are many things I want to tell you about this, the connection between gravity and fluid dynamics, and I'd like to end the last 10 minutes with some speculations. Okay, so the first thing I'm going to tell you about is something very interesting. Look, we've constructed the space-time for an arbitrary fluid flow, and now a natural question is, what are the global properties of the space-time thought of in terms of general relativity? So the question that you could first ask is, does this space-time have an event horizon? Okay? Now, of course, you know that the uniform black brane, which was the starting point of this expansion, has an event horizon depicted by this diagram, this surface in the Penrose diagram. And you might think that if you were a particle physicist, you might think that okay, you're doing small modifications about this, so there'll be an event horizon with small modifications. And you're completely right. That's the right answer. But if you were a general relativist, you might not at first think this. The reason for this is that event horizons are famously ateleological, meaning the question of whether we are now inside an event horizon or not depends on whether some big shell can come and collapse 1 million years in the future. Okay, that could pull us back, force us into a singularity. Okay, so event horizons are very non-local concepts. They're causal surfaces that separate those things that hit singularities from those that don't, and in flat space depend very acausally on dynamics. Okay? So, if that was what was going on here, it would be very hard to know whether we had an event horizon or not, and would also be pretty useless. We wouldn't be able to use the event horizon for the useful purpose that I will use it in 2 minutes. That is not what's going on here. In order to understand that this is not what's going on here, let's look at the Penrose diagram of ADS. Okay? Look, in ADS, you can think of the event horizon as separating those points which can send information to the boundary, which can send a light ray to the boundary from those that can't. But if you're in ADS and you're at coordinate r, a light ray goes and hits the boundary in a finite time. What is that finite time? That finite time is 1 over t. So 1 over r is r. Okay? And this well, it depends. If you start from the place where the event horizon is in ADS space, that finite time turns out to be 1 by t. That's a simple calculation to do. So ADS is event horizons in ADS are much more local than in flat space. You know in time 1 by t whether or not you're inside an event horizon. Nothing that happens to the future that can change it, because your ray has hit the boundary and we're finished. But remember that 1 by t is precisely the length scale that we decided to be much larger than in doing fluid dynamics. 1 by t is the mean free path of the fluid dynamics of the system. Okay? So over length scales long compared to this mean free path, long compared to 1 by t, the question of whether you're inside the horizon or not is a local question. Okay? So by doing local rather than global physics, we can determine the event horizon of this manifold. Okay? The technical device we use to do this is the following. It's actually a very simple exercise. You use the fact that the event horizon is you assume you've got a fluid flow that has some well understood asymptotics at infinite time. For instance, it settles down into the uniform black brane at infinite time. Most fluid flows probably do this because fluid dynamics is dissipative. Large time, you settle down at equilibrium. Okay? For any such fluid flow, you know what the space-time is at infinity, at t equals infinity. And then the event horizon is the unique null manifold that approaches the event horizon of this known solution at infinity. Using that idea, you can simply determine the event horizon to the event horizon surface to this space-time metric, and you find a local answer. So you find that RH is equal to pi t. The location of the event horizon is pi t as it was at 0th order as a function of x mu. Okay, plus something of order. So let's take pi t out. So 1 plus something of order 1 by t times first derivative scalars. So for instance, del dot u times something. All scalars you could write down first derivative order. Plus 1 by t squared times second derivative scalars, and so on. We've evaluated the location of this event horizon accurately to second order. The important thing is that there is a local expression that determines the location of this event horizon in terms of local fluid data. Yes?
You're saying that if you start infinitesimally close to the event horizon, that it would take a time 1 over t to reach the boundary, or?
No. I'm saying, I was trying to give you an intuitive statement here. I was saying that suppose you started in ADS space. It might even be true when you say I haven't checked that, but I was saying something simpler. Suppose you were starting in ADS space at that value of r at which the event horizon is located. Okay? Then it takes time 1 over t. I haven't actually put in going near the horizon, the time delay for that, if that's what you're talking about.
Yeah,
yes, but okay, you can make this estimate more serious in that language. Okay, so there are some logarithmic corrections to what I said. You can make this estimate more serious But so you can narrow down the location. You know, you get a certain width from this point of view. Okay, with a certain error, you can tell whether you're in the event horizon, within the event horizon or not, right? But the more serious calculation is the one that I told you about here. The event horizon is defined by a mathematical construct. It's a unique, you know, there's a mathematical statement. There's a unique null manifold that does this. We can solve that mathematical problem. It turns out to be one you can solve order by order in a derivative expansion, and just find what the event horizon is. Okay, so I can answer you, you know, how much it changes quantitatively. Yes.
The convergence is.
Okay, convergence in any of these series, I just don't know.
Yeah, but it might be that it is related when it breaks.
Yes.
Perhaps.
Yes. Yeah. The question of whether this is a convergent expansion or asymptotic, and if it's convergent, what its radius of convergence is, I don't know. The physical argument I suggest, it suggests that, we know that the event horizon is actually non-local on scale 1 by t. So you might suspect that, but I don't even know if this solution to fluid dynamics is convergent. So, okay, I just don't know what convergence. Yes?
In these corrections to RH,
What?
in the corrections to RH,
Yes.
the dissipative scalars show up, right?
Only the dissipative scalars show up.
Orders.
Is this right? I'm not sure of that.
One would expect, right?
One would expect I could. Okay, I don't have that. I don't have it here. I'm sorry. I'm sorry. I'm not sure. Okay. Now, what does this construction of the event horizon give us? It tells us that we know that our space-time is shielded by an event horizon. So it makes sense of our basic criteria to work with only spacetimes that are non-singular. Why does it do that? Clearly our spacetimes are not completely non-singular because they have the singularity of the black brane. What was different between that singularity and some other singularity that could occur in the middle of spacetime that we threw away? Well, the difference is that it's shielded by a regular event horizon. Okay? So our construction is self-consistent in that way, that it's self-consistently non-singular. Okay? However, you can do something more important and more interesting with this event horizon. With your knowledge of the event horizon, you can use it to construct a positive divergence entropy current that gravitational hydrodynamics is automatically equipped with. I'm going to explain very briefly and very, very roughly how you do that. See, in any space-time, suppose you've got an event horizon. So you've got some space-time and you've got some event horizon surface. Now, there's something that is always true of all event horizons. That is, event horizons are generated by null geodesics. Okay? That you can think of an event horizon as, I think relativists call it a congruence, family of null geodesics that together constitute the event horizon. Okay? And the vector field along these null geodesics is normal to the event horizon manifold. This is a statement that the event horizon is a null manifold. Okay? So suppose we're at some point on this event horizon and I choose coordinates so that one of my coordinates is lambda, which is an affine, which is some parameter along the generator event horizon at that point, not necessarily affine, though we could choose it to be affine. And then there are d minus 1 other coordinates ya, parametrizing which null geodesic. Okay, now you can ask, now I'm going to ask the question, what is the induced metric on the event horizon in these coordinates? What form does it take? And the answer is that this induced metric takes the form GAB dya dyb. Lambda, this last coordinate, so this runs over d minus 1 coordinates, it's a d-dimensional manifold. The last coordinate lambda just doesn't appear because it is the normal to the manifold. Because the little vector in the direction d lambda is orthogonal to every other vector in the manifold, that tells you that g with lower indices lambda, anything is 0. So lambda just doesn't appear in this metric. Okay? So this is the form of the induced metric, the metric on the event horizon manifold. Now, Hawking in the early 1970s proved an incredibly important theorem. He proved that d by d lambda of square root of this g is greater than or equal to 0. Okay, that is that the area enclosed by the area in this sense, the area in the sense measured by, of course, area is really 0, but you just take the area defined by g. The cross-sectional area defined by these null manifolds always increases towards the future, provided you're dealing with general relativity that are coupled to matter that obeys certain energy conditions. These energy conditions, now in our case we're just dealing with the general relativity coupled to a cosmological constant. You can just check whether Hawking's assumptions are true or not. They're true. So the event horizons in our that we construct have to obey this theorem. Okay? What good is that? Well, suppose we define what I'm going to call an area d minus 1 form by square root g dy1 wedge dy2 dy d minus 1 on the event horizon. Okay? Then the statement that this is greater than 0 is the statement that d, so let's call this form alpha, that d alpha is greater than 0, where I call a d form positive if its coefficient of d lambda wedge dy1 dy d minus 1 is positive. That's my definition of positivity of a d form. Okay, so I've defined a d minus 1 form on the event horizon such that the exterior derivative of it is positive. Now what I do is I take this form which is defined on this event horizon and pull it back to the boundary along the null ingoing GeoD6 that we use for our gravitational construction. This pullback defines a d minus 1 form on the boundary, which is also positive, as you can show. It's 2 lines using this definition of positivity. But the dual, the Hodge dual to a d minus 1 form is a current. And the Hodge dual to the exterior derivative of a d minus 1 form is the divergence of that current. So using this construction, you have constructed a current field, a vector field on the boundary whose divergence is always greater than or equal to 0 for any solution to Einstein's equations dual to this hydrodynamics. So we have shown that the hydrodynamics that we have constructed is equipped with a positive divergence entropy current. This should make contact with what I discussed in my first 2 lectures. You remember that from the Landauian point of view, this was one of the necessary requirements of hydrodynamics, and we've shown that the hydrodynamics that gravity gets obeys this condition. You can think of this in many ways. You can think of this as, you know, a beautiful synthesis of 2 beautiful ideas: Landau's idea of positive divergence entropy currents in hydrodynamics, and Hawking's theorem of entropy of area increase. You can also think of this as a little bit, if you were suspicious of Landau's idea that entropy had to increase locally, that there could be no global conspiracy, you can think of this as very, a vindication of his idea from a point of view that, you know, is very far from his way of thinking. Okay? So, in summary, the fluid dynamics that we've constructed is dual to regular solutions of Einstein's equations, solutions in which all singularities are shielded from the boundary by a regular event horizon, and the fluid dynamics is equipped with a positive divergence entropy current, and so must obey all the constraints that you can derive from Landau's criteria that we talked about in the first 2 lectures. Okay, any questions or comments about this before we proceed? Excellent. Okay, now for the next half an hour we'll continue about the connections between gravity and fluid dynamics. Much of what I'm going to be telling you is about extensions of this general idea, but of course I'll focus only on those those things that are interesting. Okay, now so far in the last lecture and part of this one, we've discussed the construction of solutions to Einstein's equations that are dual to uncharged fluid flows. There's a natural question. What about charged fluid flows? In fact, we spent most of the first two lectures talking about charged fluid flows. Not uncharged fluid flows were relatively boring. Okay. How do we study the fluid, the bulk dual of charged fluid flows? There's one unfortunate thing here. You see, in studying the bulk, either unfortunate or fortunate depending on your point of view, in studying the bulk dual of hydrodynamics in a conformal theory, in ADS theory, we started our discussion by pointing out that there is this large universality leading to an more or less unique two-derivative effective action, namely Einstein's equations with a negative cosmological constant. There's no such uniqueness once you generalize to more complicated dynamics, for instance, with having charged fields, with allowing charge for your fluid. How do we see this? Okay, so we see this by appealing to, okay, so firstly, what new ingredients do we need to add in the bulk in order to discuss charged fluid dynamics? This has been discussed in some language or the other 20 times in the lectures in this school. You need Maxwell fields in addition to Einstein's fields. Okay, because according to the ADS-CFT correspondence, a charge current on the bulk is dual to the gauge field of an Einstein type, of a Maxwell type gauge field in the dual to a charge current on the boundary is a gauge field in the bulk. Okay, so we need a gauge field in the bulk if we want to have a charge current on the boundary. Now, you might think that the most natural Lagrangian to write down is R plus 6 times G, so the square root plus 6 plus F mu nu. And this is a natural Lagrangian, but it is not unique. There are many ways in which it's not unique. For instance, you could put a function of a scalar behind F mu nu. Okay? This happens all the time in studies of the attractor mechanism or studies of diletonic black brains as various lecturers in this course have emphasized. Okay? When this happens, if you've got F turned on, that can source the scalar and make you have to solve more complicated equations. Okay? In fact, so the net upshot is that when we're studying charged hydrodynamics, there isn't a universal system to start with that will work for every reasonable question that you want to ask, even in known examples of ADS-CFT. So in this situation, the safest, one safe ploy is to back up to an example you do understand very well and look at the effective action that comes from there. The example that we all understand very well is n equals 4 Yang-Mills. As you know, n equals 4 Yang-Mills has a consistent truncation to n equals 8 gauge supergravity in 5 dimensions. N equals 8 gauge supergravity has an SO6 gauge field. But if you make the following further truncation, that you take SO6 and you truncate it to a particular U1, U1 in which you turn on only diagonal fields under the in SO6, so only Cartan valued fields, and choose these Cartan valued fields all to be equal. In this case, you get a further simple truncation, a truncation to the Einstein-Maxwell system with one additional term. The one additional term is a Chern-Simons term. Now, this is not the only thing we could do even within n equals 4 Yang-Mills. If we weren't interested in the diagonal U1, if we were interested, for instance, in one U1 non-zero, the other two being 0, you would be forced to couple in scalars. Okay? And this is an interesting system which has been partially studied, but clearly this is the simplest thing to do. You're keeping only the fields that are necessary for the problem that you want to solve. Okay? So here we're giving up on universality by taking a special example. Okay? Now, what is the procedure that we're going to follow here with charged hydrodynamics? Well, it's very similar to what we did for uncharged hydrodynamics. You see, the starting point for the construction of solutions for uncharged hydrodynamics was a 4-parameter set of spacetimes labeled by a temperature field and a velocity field. Very luckily, we have exact solutions to charged black branes. This is Reisner-Nordstorm black branes in ADS space. So you just play the same game, starting with a spacetime that's foliated by tubes, by tubes labeled by 5 functions: velocity, a velocity field, a temperature field, and a chemical potential field. Okay, you go through and play all the same games. It's a little more difficult. You can do it, and you get an answer. This answer was constructed independently about the same time by a group based in Germany and a group based in India. Okay, and you can find the dual to first order to second order charge hydrodynamics that comes from this particular action. Okay, once you've got the dual to this charge hydrodynamics, you can find the holographic formulas for the stress tense and the charge current, the constitutive relations. And historically, this had a surprise. You see, in the case of uncharged hydrodynamics, all the new lessons we learned, qualitative new lessons, were about the structure of the constitutive relations at second order. Because it was very well understood that at first order, a conformal fluid could only have a viscosity correction. Then there were questions about what the value of the viscosity correction was. But that this was a form in hydrodynamics, nobody doubted, and it was true. However, as I've explained in the first 2 lectures, there were, well, I don't know, but wrong, but perhaps misleading remarks in the text of Landau-Lifshitz that appeared to imply that the most general, in Landau frame, the most general J mu dis form for J mu dis was sigma times E mu minus T del mu of mu by T. But as we discussed in previous lectures, this is not the most general allowed form. There are those Chern-Simons corrections, if you remember, those things determined by those constants. Okay? And the way this was first discovered was that this calculation was done in gravity, and you found the expression for J mu dis, and it had this, but it had the additional piece. It had an additional piece proportional to omega mu, something times omega mu. Okay? This led to consternation among people who understood fluid dynamics, which at that point didn't include myself. I mean, I thought, fine, it's allowed by symmetry, what's the problem? But people like Sohn, who understood fluid dynamics, contacted us and said, no, it can't be, because it's not consistent with entropy positivity. Landau-Lifshitz have shown this. Okay, which led to the reopening of an old story, as I described to you in the first few lectures. Okay, so this is a good example of how ADS CFT can be useful for real life physics. Okay, you know what string theory has been good at is doing calculations consistently and correctly. So if somebody has a claim that he claims applies to every quantum field theory, then we can test it. In my experience, these claims often turn out to be not quite right. Okay, but the fact that the guy could make the claim meant that there was some general way of making this claim. So then you can go back and do that general thing more correctly and make a correct claim for every quantum field theory. Then this correct claim applies to QCD, and then you've made an experimental prediction, maybe. Okay, so it's very direct. It's not quite finding the theory of quantum gravity, I'm sorry, but okay, it's something. Okay, okay, excellent. That's all I wanted to say about charged hydrodynamics. Other questions or comments? Please.
On the gravitational side, that energy moment conservation, but which is one dimensional higher than the energy moment conservation at the boundary.
Yes.
So did you impose some constraint?
You know, the energy momentum conservation of the stress tense on the right hand side of Einstein's equations is automatically implied by Einstein's equations. So since we solved Einstein's equations, we have imposed it. But it wasn't something that was important. I mean, it's not like we thought through separately about what that implied.
I'm thinking you could have energy flowing in the R direction. So at the boundary, energy momentum is not strictly.
No, that can't happen because you impose normalizability. You impose that everything that could carry energy dies off fast enough at the boundary, so there's no inflow of energy from the bulk to the boundary. Good question. Other questions, comments? Yes?
Has this effect of this new term been observed in experiment?
This is a matter of some controversy. Some people, Sohn and collaborators have have suggested that some observations in the Rick experiment might have an explanation that needs the invocation of such terms. But I don't think the jury of that, I don't think we know for sure. But, just the fact that a respectable physicist has suggested that some experiment could have such means it's not outlandish. It's not today, tomorrow. Okay. Other questions, comments? Okay, excellent. So, that's all I wanted to say about charged hydrodynamics. Oh, there's one more thing I wanted to say about charged hydrodynamics. Let me say it immediately. This touches on other lectures in this school, which is why I wanted to say it. There's something that you can do with a charged brain that you cannot do with an uncharged brain, at least for Reisner Nordstrom brains in ADS space. That is, you can take the brain to t equals 0 without reducing it to nothing. Okay? You can look at extremal brains. So once you have you've got some interesting dynamics involving charged brains. Okay? There's a natural question that you can ask. Does this construction work all the way down to extremality, to t equals 0? Okay? And the answer here is sadly negative, as I will explain to you, but I will also tell you about a little conjecture about what. So let me start. Firstly, I want to explain that our construction, okay, which very nicely constructed this nice regular space-time, does not work at extremality. Why doesn't it work? Okay, if you remember, the key thing to making the construction non-singular was that we had to solve this equation. R cube f of r d by dr of an unknown is equal to some regular source. And we took this equation and integrated it. And then notice that this object here was 0, so we integrated it from the event horizon up to infinity so as to make this equation consistent with alpha being regular. And if we had uncharged black brains, it's perfectly correct. When we have charged black brains, now there's something new. You don't have one event horizon, you have two. You've got the outer horizon, the inner horizon. So now you might wonder, which horizon should I choose here? And it's clear you should choose the outer horizon, because you want your spacetime to be regular all the way up to the outer horizon. If there's a singularity at an inner horizon shielded by the event horizon, you don't care. So that's what we do to generate the duals to fluid flows in charged black brains. We integrate from the outer horizon on. But when the solution becomes extremal, the inner horizon starts approaching the outer horizon. And exactly at extremality, they touch. What does that mean? At extremality, this function f of r, which at every other value has a single 0 at the outer horizon, develops a double 0. This procedure here, integrating from horizon to something, generates a single 0. That's not enough to compensate this double 0. So even if you adopt this procedure here, the double 0 here is not compensated by the single 0 here. When you divide and do the second integration, you get a logarithmic singularity. You get a logarithmic singularity in your unknown function. So, next lesson, our procedure for charged brains works very well at non-zero temperatures, but does not appear to work if the charged brain goes to 0 temperature. Now, you might think this is a bit odd. You might, well, depending on your point of view, you might wonder whether this is a bit. Please, you have a question?
I mean, a small perturbation in your expansion.
Yes.
Would destroy the extremality.
Yes. So, really speaking, if you had this procedure would work, let's say epsilon away, but you would say that the term in the expansion would have a 1 over that epsilon. Okay. So, really, although the procedure would formally work, you would find that the series would be badly divergent, would be far from convergent if you were very near extremality. So for the series to converge, you would have to have delta t smaller than something. Now, okay, I think it was delta x is greater than equal to mu squared by delta t. That's when the derivative expansion would really work, when delta t is very small. Okay, so as you approach extremality, you would approach breakdown of the derivative expansion. You'd have to go to longer and longer distances for hydrodynamics to work, and at extremality, you would really have hydrodynamics breaking down at all length scales. Okay, okay, so now I'm going to try to interpret this for you just now. Now you might ask, why is this happening? Okay, and I'm going to give you, well, I don't know exactly, I don't know really how to fix this completely, but let me give you some thoughts. In earlier lectures in this school, you've heard a lot about computations of 2-point functions of various operators in extremal black-brane backgrounds. Okay, much of the focus was on poles that migrated to the origin. Okay, so we're looking at 2-point functions in the complex omega plane at a fixed value of k. In John McGreevy's talks, he looked at what happened to this 2-point function as k migrated to kf, and was interested in this pole as it went to the origin. And that's, those are all very interesting questions. But there's something else that's really interesting about this 2-point function that's really glaring at you, namely that there's a cut. Okay, cuts are very odd. Cuts are very odd from the point of view of gravitational computations of these 2-point functions, because singularities are supported on propagating modes, and the propagating modes outside at least finite temperature black branes are all quasi-normal modes. They occur at discrete values of omega, and so that singularity structure should be reflected in having lots of poles. What the hell is this cut? Well, in order to investigate it, what you can do, okay, so the fact that there's a cut doesn't depend on whether you're doing fermions or bosons, stress tensor, charge current. So let's get rid of this pole, let's forget about these poles. Look at the cut that happens when you go to k equals 0 as omega goes to 0 in the stress tensor. Okay, so in order to resolve what's happening, let's move a little bit away from extremality and see what happens to this cut. It turns out that this cut breaks up into a very fine accumulation of poles. What's going on? Why is this happening? Why do we get this fine accumulation of poles that becomes a cut at 0 temperature? Well, the answer is very simple to understand intuitively. You see, firstly, why were quasi-normal modes in ADS space spaced like a box, spaced with a finite spacing? It's because ADS space at finite temperature behaves like a box. One end of the box is the boundary, the other end is at the horizon. The effective dynamical length of that box is 1 over t. Okay, and so 1 over that length, namely t, sets the spacing of quasi-normal modes. You're just solving a particle in a box problem that has the spacing set by the length of the box. However, an ADS space with an extremal black hole is still a box, but the size, as you approach extremality, the size of the box suddenly starts becoming very big because of the huge tube as you approach the horizon of ADS2. Okay? So the box, as you approach very near to extremality, suddenly this box starts becoming very big, and then the box becomes bigger and bigger and bigger without end as you hit extremality. That's why the spacing between these quasi-normal modes make up the cut goes to 0 and you get a cut. Now, from the point of view of quasi-normal modes, what is hydrodynamics? Hydrodynamics is an interesting theory. You see, let's forget about these finely spaced guys for extremal black holes and think about ordinary quasi-normal modes in a finite temperature black brane for a moment. Of the infinite number of quasi-normal modes in the problem, there are 5 distinguished ones. These 5 distinguished ones are distinguished because they're massless, in the sense that omega as a function of k goes to 0 as k goes to 0. How do we see that there had to be 5 distinguished quasi-normal modes? We see this from Goldstern's theorem. A quasi-normal mode is nothing but a normalizable fluctuation around the black brane background, and at k equals 0 with no spatial variation, we know of 5 normalizable fluctuations, namely changing the temperature, changing the chemical potential, changing the velocity of the black brane. So we knew that there had to be long-lived quasi-normal modes, 5 of them. Of course, there are no more in general than are needed by symmetry. So of all the infinite number of quasi-normal modes in the problem, 5 are massless, the rest are massive. Fluid dynamics can be thought of as the effective field theory obtained, the nonlinear effective field theory of these massless quasi-normal modes obtained by integrating out the massive guys. When can this go wrong? When does effective field theory ever go wrong? Effective field theory goes wrong if you keep not all the right effective degrees of freedom. If you try to integrate out massive degrees of freedom. So if you're in a situation where new quasi-normal modes apart from the hydrodynamic quasi-normal modes start becoming massless, but you insist on integrating them out, you'll generate singularities. Okay? But that's exactly what's happening in this extremal background. An infinite number of quasi-normal modes are going to 0 mass. Okay? This is why hydrodynamics is breaking down near 0 temperature. It's because of the new light degrees of freedom that a lot of people have been excited about or complaining about in the lectures of the last few days. Okay, what can you do to replace hydrodynamics? Sounds very difficult. You need hydrodynamics coupled to conformal field theory or coupled to some other massless system. Sounds very difficult, very interesting. I don't know what to say about it, except for one thing. I have a conjecture which Jyotirmoy has just informed me he thinks is not true. But anyway, I have a conjecture, and this conjecture is that you see, suppose we have these guys who are going to condense. For what process in the can we trust? Can we deal with hydrodynamics? Well, we need an energy scale separation between the process of consideration and the mass gap of the thing that we're integrating out. But we want to do this all the way. So there's only one kind of process for which this will work, namely processes which have energy scale 0. There's only one kind of process which has energy scale 0, namely equilibrium. Okay? So for the question that I addressed in my first lecture, namely characterizing all possible equilibrium solutions of hydrodynamics on an arbitrary background manifold with an arbitrary background gauge field, my conjecture is that extremal hydrodynamics will work for that process and that process only. So that conjecture is that if you take our general constructions of hydrodynamics and specialize to equilibrium, you'll generate non-singular new extremal solutions, which sounds like an interesting statement in gravity. I don't yet know whether it's true or false. Jyotirmoy tells me he thinks it's false, but I think we need to check this. Okay? So I think that hydrodynamics, my feeling is that hydrodynamics, this kind of holographic hydrodynamics, has only very limited applicability, if at all, to extremality. That is just for the process of generating equilibrium and no dynamics. For any dynamics, you'll excite the light modes. Okay, that's all I wanted to say about. That's really all I wanted to say about charge hydrodynamics. Any questions or comments, please?
So is it true that if the geometry doesn't terminate, then it's unstable? The system is unstable.
This system is unstable. Well, unstable to what?
Perturbation in the boundary.
Well, if you just take the Einstein-Maxwell system, this system that I wrote down there, and you look at the extremal Neisner-Nordstrom black brane, classically there is no instability. Okay? Now, if there's some deeper statement of an instability that there must exist a field which will be unstable, or there's some quantum instability, some tunneling instability, this calculation can't say that. But just yes.
Why doesn't the chemical potential split these poles? I mean, the temperature.
Because it's a very good question. It's not obvious just from general principles. If you're a little bit away from extremality, if delta T is not very small, then it is true that these poles are separated by spacing given by the chemical potential. But the reason that it doesn't is this infinite throat of AdS2. The spacing of the poles is 1 by the size of the box. And the infinite throat of AdS2 means that the box size goes to infinity. Okay? So it's a matter of detail. It's a fact that this extremal black hole has this infinite throat.
Right, and it's only there because it can be extremal with charge.
Because it can be extremely with charge, exactly. Yes. Yes. Other questions, comments? Yes.
If you go beyond holography, can you argue that hydro breaks down at 0 temperature?
It's a good question. I don't know. If you look at a fluid that has 0 entropy at 0 temperature, then presumably it's clear that there's no hydrodynamics. Because hydrodynamics is based on thermodynamics, thermodynamics is based on large numbers. Okay, you need some large number somewhere to justify it. So if you look at the kind of fluid that most condensed matter people seem to like, namely those that obey this Nernst's law, presumably it's clear that hydrodynamics breaks down at 0 temperature.
Does anybody know of any quantum system, any system for which hydrodynamics applies at 0 temperature? It simply doesn't. It's not a 0 temperature theory. Sometimes when condensed matter physicists are talking about spin waves or Goldstone modes, and they write down some equation of motion of spin waves, they call it hydrodynamics. Or even Luttinger liquid, they say we're doing Luttinger liquid hydrodynamics. Unfortunately, that's terrible terminology because it's not hydrodynamics in the sense that Shiraz has been discussing. It's really effective field theory, as I mentioned.
Okay. Very good. Okay, so we have about 15 to 20 minutes left. So there are 2 or 3 other very brief review things I'm going to tell you, and then I'll try to end with some wild speculation. Okay. Okay. The next question you could ask is is all of this stuff tied to conformal invariance? This is a question we got asked a lot. Is this whole thing somehow crucially tied to conformality? And of course, it's true that conformal invariance made many things very nice. It made the starting background solution, ADS space, very nice. You had the black brains very nicely available. But the basic idea of this construction between that interplays between gravity and gauge theory, okay, is not tied to conformal invariance. And in fact, there were these very beautiful papers by Skenderis and collaborators, also by Wadia and Justin David, in which they showed something very beautiful. They showed that for all, or at least almost all near horizon geometries to the D1, it was work for the D1 brane, for the D4 brane, for at least the D1 brane and the D4 brane, D5 branes also possibly. For a large class of near horizon geometries that arise in string theory, there is a consistent truncation to the Einstein-dilaton sector. Moreover, they showed that this consistent truncation has a very simple mathematical interpretation. It can be formally obtained as a dimensional reduction of a gravity in a higher dimensional ADS space, compactified sometimes on a fractional dimension. Okay. So in certain cases, well, it means you have to put the right powers of, you've got some field outside there. Meaning, you know what it is in 1 dimension, 2 dimensions, 3 dimensions, do it in n dimensions, and then just continue n to be a fraction. It's like dimensional regularization. Okay? Now, the reason this is interesting is that, as I've explained, we have a procedure for generating the dual to hydrodynamic flows in ADS theories. Okay, and you just get the theory by compactification, by dimensional reduction of Einstein action with a negative cosmological constant. Okay, we have a way of generating these hydrodynamical flows. I showed you the example of ADS5. It was simple to generalize to arbitrary ADS spaces of arbitrary dimension. You combine this observation by the observation of Skenderis and collaborators, and you reach the following conclusion. The hydrodynamics of, let's say, the D4 brane, okay, can be obtained by a dimensional reduction of one of the hydrodynamics we worked out of some higher dimensional ADS space. Okay, and the statement is just true and can be checked in many ways. Now, I emphasize that the dimensional reduction of a conformal hydrodynamics is not conformal. So, for instance, if the trace of the stress tensor in some higher dimensional space is 0, it's not 0 in the lower dimensional space because you're not taking the trace over those indices which you've thrown away. Okay? So, you generate interesting non-conformal hydrodynamic equations this way that apply to the D2 brane background, for instance. Okay? Just by dimensional reduction of well understood systems that we've talked about before. Okay? I don't really know what all this is, what the fundamental reason for all this working is. In the case of the D4 brane, it's probably just the fact that it's the D4 brane is the M5 brane on a circle. But it works for more examples than can be explained in this manner. I don't know why it's working so well, but what it tells you is that for basically for most near horizon geometries in string theory that we love, we know how to generate the hydrodynamic expansion, and we can find all transport coefficients by a two-line procedure from the conformal case. Okay, so this is, I mean, it's far from the most general example, but this is just one example of non-conformal hydrodynamics that you can generate by this process. Of course, it turned out in the end to be almost very simply related to conformal hydrodynamics, but that didn't have to be. Okay, that's just a trick. Otherwise, if that wasn't the case, you could have gone through the hard work of solving the equations again. Okay, there's another non-conformal situation that you can study that I will not talk about in very much detail, but that also turns out to be very simply related to conformal system, and that's a Witten-Schurk-Schwarz compactification of, let's say, the D3 brane. So suppose you Schurk-Schwarz compactify the D3 brane, you find the dual of a confining two-dimensional theory, perhaps a confining two-dimensional quote-unquote gauge theory, some confining two-dimensional theory. And you can ask, what is the dual of the hydrodynamics in this theory? Turns out the answer is really trivial, because for those of you who know the story, the high temperature solution to Witten-Schurk-Schwarz compactification is simply the D3 brane metric, the thermal D3 brane metric on a circle identification. So this hydrodynamics also turns out to be simply the dimensional reduction of the D3 brane hydrodynamics, which we worked out in these lectures. Okay, it's a bit disappointing that you don't get too much new, but anyway, so this is an example. There's an interesting story about domain walls in such Schurk-Schwarz compactifications, and extending this study to hydrodynamics with walls. These walls are the walls of what sometimes are called plasma balls. And there's a whole interesting direction there, but we don't have the time to talk about that. Okay, excellent. The last review topic that I want to briefly mention. Okay, sorry. First, questions or comments? Questions or comments?
Can you characterize when a non-conformal hydrodynamics cannot come from a conformal hydrodynamics? Can you reverse this? Or what's the abstraction?
Well, I suppose you have to say what you mean by come from. If by come from you mean dimensional reduction, I think it's very easy to characterize that.
Okay.
Yes,
so
but
it's all very, very special.
Very special. Yes. Yes. Okay. Now, for instance, in all of these, the free energy will be some power of the temperature. It won't be the power that gets dictated by your dimension. You see, dimensional analysis tells you that the free energy of the pressure is T to the power D. If you get something from dimensional reduction in alpha dimensions, you get T to the power alpha, which won't be T to the power the dimension you're looking at, but will always be some power. In general, you will have length scales coming in a more non-trivial way than having a power. So that's an example of it. Okay. The last little review thing I'm going to tell you about very briefly, it touches upon something that Sean talked about in today's lecture very briefly, namely these gravity duals to superconductivity, or perhaps more, a purist might want to say superfluidity. Okay. Now, as Sean mentioned, there are gravity solutions dual to black branes with condensates of charged scalar fields. Okay, This was a bit of a surprise, but it seemed to violate folk no-hair theorems. It was pointed out by Gupsa that these exist, and there was, over the last 3 or 4 years, these solutions have been studied in great detail. What Sean didn't have the time to mention is that these black-brane solutions with condensates of charged scalar fields have more moduli than ordinary black-branes. Ordinary black-brane solutions in 4+1 dimensions come with 5 moduli. The moduli are the chemical potential, the temperature, and the 3 velocities. These black-brane solutions can be generalized to include a constant, to include a gauge field, a spatial gauge field that goes to a constant at infinity. The spatial gauge field is not pure gauge because of the presence of the condensate at the back. Okay, and this new modulus has an interpretation. It has the interpretation as the superfluid velocity. Okay, so these superfluid solutions come with 8 parameters, an 8 moduli set in 4 dimensions, labeled by 3 velocities, 3 superfluid velocities, a temperature and a chemical potential. Okay, so you could in principle, and it's a much harder game and you have to do much dirtier things, but you could in principle take this 8 parameter set and do a construction on it. Do this tube wise blah 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 and generate a set of equations of motion. And the first really beautiful, the only really beautiful result in this game was by Sonner and Withers 2 years ago, in which they showed, without having to solve any equations, that just by using general, the kind of general manipulations that allow you to show the first law of thermodynamics and general relativity, they showed in this very beautiful way that the form of the perfect fluid stress tensor for this superfluid hydrodynamics is exactly the form predicted by Landau and Tisa in the 1950s, even though Tisa didn't understand what he was doing. Okay. So this story, in a very general and beautiful way, generalizes to the equations of perfect superfluid hydrodynamics. The story can be now the study of superfluid hydrodynamics with dissipative corrections is a more murky one than perfect superfluid hydrodynamics, and in a very painful paper that I don't recommend anyone read, my group as well as Amos Yarom's group he was then in Princeton, performed very painstaking calculations to determine the structure of first order corrections to the superfluid hydrodynamic equations in a particular model, in a particular parameter regime. There were about 4 expansions in that paper. It wasn't a pleasant story, but there was a payoff. The payoff was the kind of payoff we've seen before. If somebody has made some general claim about something that has to apply to every quantum field theory, then it should apply to whichever dirty limit you study of something good. So you can test general claims against your calculations. The general claims that we tested against were the claims by a physicist called Puterman, who claimed to have the most general equations of superfluid hydrodynamics, preserving parity depending on 13 parameters. It was almost right, but not quite. Our results didn't fit in that framework. We went and redid his calculations, found he'd missed a parameter. Okay? So once again, ADS CFT to the service of humanity. You find new parameters. Okay? So this is how ADS CFT played into that superfluid game. And once you've done this, like in the case of parity violating hydrodynamics, you can go back and try to understand the formulation of superfluid hydrodynamics a bit better than has been done before. And that's still a work in progress, I would say, but there's something interesting there. Okay, I don't think that's a closed story. Okay. I think that's it for my review of content. I'll pause here for questions and comments, and then if I have 2 or 3 minutes right at the end, I will end with some. Yeah.
Is this story done for non-relativistic, let's say, Schrodinger metrics, to address your question about non-conformal fluids?
Okay. Yeah. Now there are those. Is it Schrodinger? There are those metrics that Mukund and collaborators found by null compactifications of ADS. In those cases, it can of course be done because you take the construction and follow through the null compactification. So in those cases, it has been done. In more general cases, I'm not aware. Maybe someone here knows. Mukund and collaborators have one paper on this. Mukund, Herzog, and maybe somebody else has one paper. Mukund Rangamani. Okay. Other questions or comments? Okay, excellent. Okay, so now just to end this this series of lectures, I'm going to end with a speculation. It shouldn't be called a speculation. Just a thought. Okay, thought that I find interesting. It's most likely wrong, but anyway, I find it interesting, so I'll entertain you with it for the next 3 or 4 minutes. Okay, the thought goes as follows. Look, in the first 2 lectures, we were studying the equations of hydrodynamics, and in studying those equations, we first tried to write down all possible constitutive relations consistent with symmetries. And if you were an effective field theorist, you would have stopped there, at least. If you were my kind of effective field theorist, you might have stopped there. Well, anything allowed by symmetries will be generated somehow by some theory. Why not? But the first 2 lectures were meant to convince you that that was completely wrong. Okay, there were terms and constitutive relations that were perfectly allowed by symmetries, but were not allowed by other physical considerations. The 2 considerations that we studied in great detail were A, Landau's consideration of the demand of having a positive divergence entropy current, B, the existence of thermodynamic equilibrium. Okay, and in the examples that we looked at, these 2 were all the same. The 2 constraints we got were the same, so we had some confidence that they were both correct, and perhaps even complete. I'm not sure. Okay, now, first, just at the level of a vague association, if you think about this game long enough, it's hard not to wonder whether this statement might also be true of gravity. You see, gravity, uniquely among all the fundamental interactions of nature, plays a dual role, has a dual character. It behaves like a fundamental theory in the sense that you scatter 2 gravitons, that's like scattering gravitons, that's like scattering gluons in QCD. It behaves like a fundamental theory. It has quanta that you can try to quantize and so on. However, it also behaves like a thermal theory. It behaves like Boltzmann's equations, in the sense that in certain situations with horizons, it carries entropy. And the entropy always increases. And gravity, in this extremely beautiful manner seamlessly transits between its fundamental split personality and its thermodynamic split personality. Without having to coarse grain or do any of those ugly things. Just the same equations just suddenly produce a horizon, the horizon grows. Okay, so we have seen one example, namely the equations of hydrodynamics, of a theory whose constitutive relations are constrained in a manner that goes beyond symmetry, are constrained in a manner that is constrained by thermodynamic considerations. Could the same be true of gravity? Could it be that the principles of thermodynamics constrain possible corrections to Einstein's equations? Now, what do I mean? I'm not terribly sure what I mean, but let me say a few things. Okay, as we all know and as we've used in this lecture, Einstein's equations are equipped with a beautiful theorem, the Hawking's theorem of area increase. Higher derivative corrections to Einstein's gravity have a clean notion of entropy in equilibrium. This is Wald's beautiful work, generalizing Hawking's idea. However, Wald found his formulas for Wald entropy by demanding that this entropy obey the first law of thermodynamics. The first law is only one of the laws of thermodynamics. The one that's really important for dynamics after you have the first law is the second law. Does the Wald entropy satisfy the second law of thermodynamics? Does it do it always? The answer to this question is essentially unknown. There have been many attempts to prove that Wald entropy under appropriate circumstances obeys the second law of thermodynamics. These attempts have so far not been uniformly successful. Okay, now there are two possibilities here. Okay, there are two possibilities. The first possibility is that, and maybe it's most likely, that at least for small deviation around Einstein's equation, so in an expansion in derivatives around Einstein's equation, which is all I'm concerned about. Okay, if you go off to terms to a place where two derivative terms are as important as one derivative terms, as far as I'm concerned, you're in fairyland. Okay, so in a derivative expansion around Einstein's equations, it's certainly possible that there is a walled entropy increase theorem, in which case every higher derivative correction to Einstein's equations in a derivative expansion around Einstein's equations appears to obey the consistency requirements of thermodynamics. But could it be that this is not true? That the reason that nobody has proved a walled entropy increase theorem is that it doesn't exist for an arbitrary alpha prime correction to Einstein's gravity, but that the requirement that one such exists constrains possible corrections to Einstein's gravity. Sounds way out, sounds possibly unlikely, but I'm not sure that it's not true. If it were true, it would be a new principle from low energy physics to constrain possible corrections to Einstein's gravity, and that would be very important. It's probably not true, but I thought I'd end with an entertaining thought. Okay, thank you.
String theory has some very particular high derivatives.
Exactly.
Is anything known about?
No, even for those things, there's no theorems either way. So if this idea, which is I emphasize very unlikely, but if there's something correct about it, then what would have to happen is that there are some constraints which every compactification of string theory obeys. But there are some terms that you can never get by string theory compactification, perhaps, which won't obey it. It's what Waffa and company a few years ago called the swampland. Some effective actions that cannot be obtained by consistent truncations. When I gave a version of this talk to Seiberg, he started talking about ways, if what I'm saying is true, then you should be able to somehow prove a walled entropy increase theorem by doing some manipulations on the world sheet of the string. And he had some ideas about that and so on. So, I mean, it could be that you could prove that every string theory has it, but not every theory. Okay, most likely there's nothing to it. Most likely this is just entertainment.
Other questions?
What about turbulence?
What about turbulence? Yes, what about it? Okay. Well, I'll give you my prejudice. I haven't thought terribly deeply about the subject. Well, firstly, I'll tell you what the interesting question. Have we talked about this one? No, we haven't. The interesting questions about turbulence, as I understand it from the people I've spoken to. Okay, if there are some experts here and I'm saying something wrong, I'd love to be corrected. Okay, but the people I've spoken to who claim to know about turbulence tell me that there is evidence of universality in turbulence. By which I mean that you set up a turbulent flow. Doesn't matter how you set it up. Doesn't matter whether you're using air or water, blah blah blah. Doesn't matter whether you're using cylindrical geometry or independent of how you set it up. In what they call the region of fully developed turbulence, if you compute v to the n at 0, v to the n at x, expectation value you find x to some alpha. Firstly, what do I mean by expectation value? Of course, we're in classical physics here, so there's no fundamental expectation value. What we mean is a time average. These velocity fields appear to jiggle around very much. You compute at many time steps and at time average. You find this, and the people I speak to, and I believe there's some controversy about the statement, but some people claim that that there's good evidence that these coefficients are all universal. If that's the case, turbulence is a great problem because there is an infinite number of universal numbers, one for every value of n, that is begging to be computed by a theorist. Okay, one of these values has been computed by Kolmogorov. I think at n equals maybe 3, using very clever, perhaps a deep argument, and that agrees experimentally with experimental results. Kolmogorov also gave what was effectively a mean field theory to compute all the other coefficients, but his prediction for the other coefficients don't agree. Okay, so there's a beautiful problem for a theorist. Compute an infinite set of universal numbers. That sounds like a great problem. But everyone's known that this is a great problem. It's been a great problem for 50 years and nobody's made any progress. So that's about turbulence itself. Now, you may be asking, what can ADS-CFT say about turbulence? There are two questions here. One question is, can you embed turbulence within our constructions? I haven't completely thought this question through, but I think the answer is yes. Okay, I don't think there's an issue there. However, the more interesting question is, can you learn anything about turbulence from our construction? Nobody's managed to do it so far, in my opinion. But if you do, I'll tell you what might be the reason. You see, what's really nice about ADS-CFT is this extra dimension. This extra dimension in many processes in ADS-CFT separates scale. So, if there is a sense in which the bigger vortices of turbulence live lower down in the geometry and the smaller vortices live higher up, so that this geometrical way of thinking inspires an approximation scheme that allows you to decouple things in some approximately local manner. I'm talking completely in the air. Maybe that will help you understand this physics. But if you ask me to bet, I would say not. You see, my experience, string theory is good at doing good things formally. Turbulence is too much like a real world problem. String theory hasn't had that much success with such things so far. Yeah.
You mentioned these coefficients were universal in the sense that they're the same for different fluids, or they're the same for different...
Well, they are the same for different fluids, but that's for a trivial reason. We're always dealing with fluids that obey the Navier-Stokes equations. So
they're the same for different flows.
Yeah. So turbulence, firstly, there's a non-trivial statement here. The turbulence is supposed to be captured by the Navier-Stokes equations. Okay, not by the short distance cutoff that cuts off all these Navier-Stokes equations. Okay, so that's an interesting non-trivial claim here, which is supposed to be true. Okay, given that it applies to different fluids in regions where you can ignore the compressibility of all of them, is obvious. What's really the content of universality is you set up a flow by stirring this way, or you set up a flow by sending through a pipe. That's all the same. But I should say I'm very far from being an expert on turbulence. So everything I say on turbulence, if somebody knows better, I should be corrected. Even that I don't know. Alpha is negative. I'm sorry. I will back off on questions on turbulence.
Other questions? Okay, well, let's thank Shiraz for an inspiring